This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the instruction set of 8086 related to data transfer instruction under Microprocessor and Microcontroller course. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals, authors IARE and K.M. Butchandi, publication Tata McGraw-Hill Education. In 8086 processor, there are various types of instructions which are supported by the 8086 processor. These instruction categories are data transfer instructions, arithmetic instructions, logical or bit manipulation instructions, string instructions, control transfer instructions, processor control instructions, and flag manipulation instructions. Under this, first we will see the data transfer instructions. The data transfer instructions are used to transfer the data from the source operand to the destination operand. Following are the list of the instructions under data transfer instructions. The first one is instructions to transfer a byte or word. For this we have instructions move, push, pop, exchange, translate, XLAT. Next one is instructions for input and output port transfer. That is a reading of a port through in instruction, write to a port using out instruction. Next one is instructions to transfer the address. The various instructions under this category is load effective address LEA, load data segment register LDS, and load extra segment register LES. Last one is instructions to transfer flag registers. Under this we have LAHF, SAHF, push F, and pop F. First we will see the move instruction. The move instruction transfer the instruction from data from one register or memory location to another register or memory location. The syntax of the instruction is MOV, a destination comma, source, where the destination can be a memory or a register, whereas the source can be a memory or a register or an immediate data. In immediate data addressing mode, a segment register cannot be a destination register. So here we have two violations which are not supported for move instruction is, the first one is the direct data, that is immediate data, we can't load into a segment register. The second constraint we are having is memory to memory allowed is not allowed. Few example for move instruction is MOV AL comma BL. So here the source is a BL register and the destination is AL register. Using this instruction, we can copy a 8-bit data which is present in BL register into AL register. It is a 8-bit transfer. Next, move CL comma 14H. Here 14H is an immediate data that we are going to be loaded into CL register. The next instruction example is move in square braces BX comma AL. So here the source is AL register and the destination is a memory location whose address is specified in BX register. This instruction will copy the contents of AL into the memory location whose address is specified in BX register. Next, move BX comma in square braces SI. Here the source is a memory. This memory contents we are loading into BX register. So BX is loaded with the memory contents whose address is specified in SI register. So this is a 16-bit data transfer as the destination is a BX register. Next, the constraint is we can't load the immediate data into the any segment register. Either it can be a code segment or data segment, stack segment or extra segment. So move ds comma 5000h. This is not permissible. It is a invalid because immediate data loading into segment register is not allowed. So now if I want to load an immediate data into the segment register is we have to go in 2 steps. First, load the immediate data into any GPR, that is AX. AX is allowed for transferring the data into segment register. Then move the AX content into DS. So this 5000H location, that is data, we are going to be loaded into AX register. From this AX, it will be loaded into DS. So DS loading with 5000 is not allowed. So for this, you can go for these steps. The second one is a push instruction, which is push the contents to the stack. Here stack is nothing but the top of the stack. The push instruction pushes the content of the specified register or memory location onto the top of the stack. The stack pointer is decremented by 2 after execution of the instruction. The actual current top of the stack is always occupied by the previously pushed data. Hence, the push operation decrements the stack pointer SP by 2 and then store the 2 bytes contents of the operand onto the top of the stack. When we are placing the data onto the top of the stack, first the higher byte is pushed and then the lower byte will be retrieved. Syntax: push operand 1, where the operand 1 can be a memory location or a register. In immediate addressing mode, this is not corresponding to push. So let us consider we have a push AX. The first instruction which we are going to have is push AX. The top of the stack is pointing to the location, which is the stack pointer will have the address is FFFF. When we have pushed the content of AX, first AH content is placed followed by AL contents. Then if you are writing push DS, on the top we are going to have DS, which is 2 memory locations. On the top again you can have the memory data you can place. The next instruction is pop instruction, which is for pop the contents from the stack. The pop instruction, when executed, loads the specified register or memory location with the contents of the memory location of which the address is formed using the stack segment register and stack pointer. So here the pop is retrieving the data from the stack. For every stack operation, the stack pointer will be incremented by 2. The pop instruction serves exactly opposite to push instruction. The syntax of pop instruction is pop operand 1, where the operand 1 can be a memory location or a register. Few example is pop AX. So now when we are execute this, so first the top of the contents will be popped into the AX register. If you have an instruction is pop DS, the contents of DS will be loaded into the stack already. Those contents will be retrieved back into DS. Suppose if you have an instruction push AX, then followed by push DS. In the top of the stack, this is initial top of the stack. Now AX will be loaded to here. Now your TD top of the stack will be pointed to here. Now then we are going to have DS. What is the order which you are placed later, that we have to retrieve first. So when you do push operation for AX first followed by DS, when you do the pop operation, first we have to do pop DS then followed by pop AX. Because the stack memory will go for last in first out scenario. The next instruction is for exchange. The mnemonic is XCHG. The XCHG instruction exchanges the contents of the specified source and destination operands. The syntax of the instruction is XCHG destination comma source. Here the destination can be a memory or a register. The source can be a memory or a register. So for all the 8086 instruction, most of the cases memory to memory is not allowed. So for exchange also, exchange of contents of two memory locations is not permitted. Next, immediate data, one of the operand, either it can be a source or destination, it cannot be immediate data. Few examples are exchange AL comma BL. Now the contents of BL will be exchanged with the contents of AL. So after executing this instruction, AL contents will be placed in BL, BL register contents will be placed in AL. So it is same as sort of a swapping of the data. Next, XCHG in square braces BX comma AL. This instruction is used for copying the contents or exchanging the contents AL to the memory location and memory location contents into AL. Next, XCHG BX comma in square braces SA. The source is a memory location, destination is a register. So from memory to register, that is BX register, the exchange of the data will be takes place. Next instructions are related to the IO ports. The first instruction is in, that is input the port, which is nothing but a reading a port. The in instruction is used for reading an input port. The address of the input mode may be specified in the instruction directly or indirectly. By default, the data whichever you are reading, that will be copied into AL register or AX register depending upon either it is a 8-bit data or 16-bit data. The DX register is the only register which is allowed to carry the address of the port. Syntax of this instruction is in AL comma port address, where the port address you can specify directly in the instruction, or you can specify the port address in DX register. That DX register directly you can write in the instructions. So once this in instruction is executed, whatever the IO device which is connected to the port address which is specified in DX register, that contents are read into the AL register. Example, in AL comma 003H. Now here 03H is the address of the port. So whatever the IO device which you are connected to the port address 03, from that IO device the contents are read and it will be loaded into AL register. Next one is a DX register. If I want to move the address into any register, that I can write move DX comma 0800H. So here 0800H is the address of the port that we are going to be loaded into DX register. Then we will raise the in instruction, the in AL comma DX. Now the contents of the IO port whose address is specified in DX register, those contents will be loaded into AL register. The next instruction is out instruction, which is output the port, which is nothing but writing a data to a port. This instruction is used for writing the data to an output port. Output port address may be specified directly or implicitly in DX register. The contents of AX or AL are transferred to a directly or indirectly addressed port after executing this instruction. The AL and AX registers allowed destinations for 8-bit or 16-bit data. No, this is not destination, source. DX is the only register allowed to carry the port address. The syntax of the instruction is out port address comma AL. So now this instruction will fetches the content of AL into a IO port whose address is specified either directly or indirectly. The port address either we can mention directly in the instruction, otherwise through DX register. Few examples for out instruction is out 03, AL. So here the contents of AL register will be copied into the IO port whose address is 03H. Out DX, AX. Here the contents of AX registers will be copied into the port whose address is specified in DX register. So for that you will write move DX, 0300H first, then you will write out DX, AX. The next instruction is LEA, which stands for load effective address. The load effective address instruction loads the effective address formed by the destination operand in the specified source register. This instruction is more useful for assembly level language rather than for machine language. If we have a data segment, this data segment is consist of some operands like operand 1 and operand 2 and some variable sum. So this is what our data segment. Now I want to know what is the address which is assigned for operand 2. What is the address which is assigned for operand 2? So for that we can use LEA instruction for fetching the address of the operand by using the LEA instruction, SI, operand. This will fetches the address of the operand and it will be loaded into SI. Assume the default address is 0000 for operand 1, 0002 is operand 2, 0004 is sum. I am taking each and every data is 16-bit size. So after executing this instruction, what could be your SI value? So for operand 2, what is the address we are having? 0002, the starting address, 0002. Example for LEA instruction is LEA BX, ADR. So here the address, which is nothing but offset in the data segment for ADC, will be transferred into the register BX. LEA SI, result. Result is a variable name in the data segment. The effective address, that is index offset value, we are going to be loaded into SI register. The next instruction is LDS or LES, load pointer to data segment or extra segment. This instruction loads the data segment register DS or ES register, that is extra segment register, and the specified destination register in the instruction with the contents of the memory location specified as source in the instruction. Syntax of the instruction is LDS register, offset address. For LES, LES register, offset address. The difference in these two instructions is which register we are loading. Either it is data segment or extra segment. If it is data segment, we are going to use LDS. If it is extra segment, we are going to use LES. Now we will see this one with respect to one example. Let us consider we have a instruction LDS or LES, anything, BX, 5000. When we have a instruction like LDS or LES with the BX, 5000H, from 5000H, 16-bit data will be copied into BX register. The next 16-bit data will be copied into either DS or ES depending upon LDS or LES instruction respectively. Why it is taking two memory location is BX is 16-bit size. As we know, each memory location is 8-bit size. Two memory locations it is going to take for BX register. 5000H location contains, assume if it is XX, that will be loaded in the lower byte of BX register. The next memory location contains, which is YY, that will be loaded into the upper 8 bits of the BX register. After 5000 and 5001, the subsequent memory location contents, which is of 16-bit size, that is two memory locations, will be copied into either data segment or extra segment. When we are copying these contents, always the lower address will be copied into lower byte. The next memory location contents will be copied into upper byte. This is for copying the contents from 5000 location into two registers. One is the register which you have specified in the instruction, that is BX. The second one is DS or ES, depending upon either it is LDS instruction or LES instruction. The next instruction is LAHF, which is for loading the contents of AH register from the lower byte of the flag register. The LAHF instruction loads the AH register with the lower byte of the flag register. As we know, the flag register is 16-bit size, that is bit 0 to bit 7 and bit 8 to bit 15. This is what the flag register contains. So whatever the contents are there in the lower byte, that is from B0 to B7, these contents are transferred into the AH register, as AH register is a 8-bit register. This instruction is used to observe the status of all the conditional flags except overflow flag at a time. So conditional flags like zero flag, carry flag, sign flag. So these are the things which we can check, which will be there in the lower byte of the flag register. The next instruction is SAHF, which is for storing the contents of AH register to flag register. So now here the source is AH contents and the destination is a flag register. Out of this flag register, only B0 to B7 to B0 will be updated. So the AH contents, which is of 8 bits, that will be loaded into the flag register in the lower byte. The upper byte of the flag registers will not be changed. So the SAHF instruction sets or reset the condition code flags except overflow, that is in the lower byte of the flag register, depending upon the current corresponding bit positions with respect to AH register. If a bit in AH register is 1, the flag corresponding in that position will be set, else it is reset. This is a 0 operand instruction. Syntax of the instruction is SAHF. The next instruction is push F, which is push the flag contents onto the top of the stack. It is also 0 operand instruction. The push flag instruction pushes the flag register onto the top of the stack. When we are placing the contents on the top of the stack, first upper byte will be placed, followed by lower byte that will be placed in top of the stack. For every push operation, as a flag register is 16-bit size, it is going to occupy 2 memory locations in the stack memory. That's why the stack pointer always will address, or it is point to the higher address. So for every push operation with respect to flag, it is going to be decremented by 2. The general operation of this instruction is similar to push instruction. The difference is which operand we are moving on to the top of the stack. Push, any register or memory location contents we can push on top of the stack. When it comes to push F, only the flag register contents will be placed onto the top of the stack. The next instruction is pop F, which is pop the flags from the stack. The pop flags, the pop F instruction loads the flag register completely, both lower byte as well as higher byte from the top of the stack. The top of the stack mainly addressed by the SS and SP register, stack segment and stack pointer. For every pop operation, as we are retrieving the data from the stack pointer will be incremented by 2, because the size of data which we are going to take here is 16-bit size. The syntax of the instruction is pop F. So when you write a push F instruction, the contents of flag register are copied onto the top of the stack. When you do pop operation, this is for push F. When you do pop operation, the contents of the top of the stacks will be copied into flag register. So these are the instructions related to data transfer instructions which are supported in 8086 processor. So the data transfer instructions, it is for mainly copying the data from one point to another point. Various instruction under this category we have studied is move instruction. The syntax of the instruction is MOV destination comma source. The source contents are copied into the destination. Here, the source can be an immediate data or register or memory location. The destination can be a register or memory location. Two violations are there here. Memory to memory transfer directly is not allowed in a single instruction. Immediate data to the segment register also not allowed in a single instruction. The next instructions we have studied is a push instruction, which is for pushing the data onto the top of the stack. The next one is popf, which is for popping the content of the top of the stack into the operand which was specified in the pop instruction. Next instruction is related to reading a port and writing a port. In instruction is used to read the data from a IO device which is connected to the port. Out instruction, it is used for writing a data to a output port which is connected to any one of the port. Next instructions corresponding to LEA. LEA stands for load effective address. This is used for fetching the offset value of a particular operand in the data segment into the target register. The next instruction is LDS or LES, which is used for loading the data segment and extra segment along with the register which was specified in the instruction from the memory which you have specified in the instruction. Next instruction is LAHF, which is for loading the flag register contents, that is lower byte, into AH register. SAHF, it is for storing the AH register contents into the lower byte of the flag register. The next instruction is push F instruction, which is to push the contents of the flag register onto the top of the stack. For every push F operation, the stack pointer will be decremented by 2. Pop F, which is pop the contents of the top of the stack onto the flag register. So pop F instruction, after every pop F instruction, the stack pointer will be incremented by 2. Thank you all. So this is the end of the session related to data transfer instructions which are supported in 8086 processor. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.